say, we're all in for a huge treat tonight. With any presentation of noise is worth watching. Some people here might have seen him present, or certainly perform. But my experience with Hanoi was I first met him coming from Foot, day one of freshman orientation, and walked into our room in Durfee D31 and found that even though he'd been living there for the past like 4 nights, the furniture was untouched. His bed was in the middle of the room, he'd been sleeping on it without putting sheets on it, just like a sleeping bag or something. And I'm like, what's going on? He's like, oh, I didn't want to choose a bed until I met you and made sure that you were okay. Yeah, so I told him he was lucky it wasn't the other way around because I would have taken the best one. So shortly thereafter, our freshman year, some of you might have been familiar with the band Sweet Spot, of which I was also Hanoi was the powerhouse behind that. And has just been involved in a remarkable number of academic musical achievements at Yale. So I'll get the resume stuff over with so we can talk more about him as a person. But Hanoi really has an incredible list of accomplishments so far. He's also a published author and presented a paper in Paris at the beginning of the summer. I don't believe on this topic. He's been involved in a number of different projects. He also was in a conference in Greece and missed a whole week of class, or like a couple weeks ago. I know because I filmed all of his classes that I was in with him. So Hanoi, the projects that I've seen Hanoi do have just grown and kind of, he's basically followed wherever his interests went and plunged forward with such courage and such creativity. And someone who I think has really made a whole, we tried to make the most of the environment we're in. He's someone who's, I think, really made the most of his academic and musical advisors and resources at Yale. Even in his majors that he stuck with, despite having to form his entire schedule his sophomore year to make sure none of his required classes conflicted. I thought it was worth it to really get a foundation in physics and continue to study music, as he always has. But so I've watched Hanoi come from freshman year. He was very into DJing. Many of us have seen him as a DJ. He DJed actually at the Spring Fling that year, and very quickly moved on, focused more on composition, and then eventually became aware of signal processing, which is now he's told me that if he could do it all over again, he would major in electrical engineering, because the things he's doing, as you'll see, is very much engineering, some of it as opposed to physics. And actually, it's funny being in several physics classes with him. The things that he whispers to me are all about music, not about physics. The way that Hanoi is a concept of these two disciplines that he bridges so effortlessly is just is very inspiring to watch with such passions as Hanoi. He's writing down physics equations and he's thinking music. He's playing music and he's thinking of differential equations or technology or coding. So other examples of the projects that I've seen him do. Well, you'll see this. I don't want to spill the beans or anything, but former projects that he's done. Let's get a sense. Well, he composed for the Yale Jazz Ensemble. What we were hearing, I think, is an excerpt of a piece that I heard performed in the Yale Art Gallery, which was for cello and electronics, using a 360-degree conical speaker that Hanoi built, trying to mimic the way that we actually perceive sounds, which is coming from all around us. So he built a speaker using a wooden bowl, went to the CEID and cut holes in it to put speaker cones, programmed it so the sounds would interfere with each other, and made a speaker which he now uses in his room as a speaker. So that's just the type of ingenuity that Hanoi has pursued, and I just have to say, I'm really looking forward to this performance and presentation of what I heard a little bit of last night and last year when he was working on it. And I'd say, let's put our hands together for Hanoi and welcome him.
So I'm really excited to be presenting on surrogate soundboards for novel transmission of instrumental audio. It's a really long title, but basically what it is is a stringless violin. So with that, we'll start off first with a musical demonstration, and I'd like to invite to the stage Tom and Rita. I can be a music stand.
We have one, you know.
Oh, that would be great.
Yeah. We don't have to be the music stand and the production.
It is quite hard doing both.
Yeah,
So while we're waiting for the music standing, so Rita and Pong, all three of us are international students from Thailand. And the cool thing is we went to the same high school.
Oh, wow.
Yeah.
And we're both in Morse. You can pass, so not too far.
It's not too far away. But we're all we're all very interested in science and music. Pong has been doing some really, really awesome things, bridging the two fields together too.
pretend you don't know where this came from.
And I'm really excited and happy to have them here presenting them. All right, thank you very much. Cool. So this here is a working prototype of the project that I've been working on for my senior project in applied physics. For this project, I am co-advised by Professor Roman Kutz and Professor Larry Violin, who are sitting in the back there. And the thing is, Yale is such an amazing place for music, both to study and also to experience and listen to music. Just a few weeks ago, I was listening to Beethoven's Fourth Symphony, played by the Yale Philharmonia in Woolsey Hall, and also listening to the composition by renowned American composer John Adams. Rita plays in the Yale Symphony Orchestra, and coming up very soon is the YSL Halloween show, which I'm sure many of you are going to go to and really enjoy. And Paul also plays in Berklee College Orchestra. D-Pops. Paul also plays in D-Pops. And Yale is just bursting with music. And so I was thinking, well, I'm getting all these wonderful opportunities, all these beautiful music opportunities at Yale. What if I want to share this with the community outside Yale? What about my friends back home in Southeast Asia, my friends back home in Thailand, who haven't had the same opportunities to come study in the United States? What if I wanted to share this music with them and share this wonderful music with the community outside of Yale? Well, probably what will happen is I would direct them to some kind of link to maybe a YouTube site, or for example, the Yale School of Music has a live stream of all their concerts, and they probably just watch the concert through that. That's where the problem starts. How many of you have watched a live stream of a concert, or maybe a recording of a concert on YouTube, and it was just perfect? You felt like you were there. Why even bother go out to a concert where you can just sit in your, your dorm room, turn on your computer, and it's exactly the same? I'm guessing not. And that's mostly, so we all know that listening to a concert, listening to a recording of an instrument, or some kind of live musical performance, when we listen through it to maybe through digital means, it never sounds the same. Listening to a recording of an instrument never sounds like listening to the instrument being played live in front of you. And that is mainly due to differences in the way that an instrument works and the way that a speaker works. Because when you listen to a concert through your computer, or you listen to a concert through your phone, you're experiencing the sound through speakers. And the physics of speakers and the physics of instruments are very, very different. And a lot of the reason why these two experiences, listening to a concert through a computer, or maybe some kind of recording or a live stream, never sounds like the real instrument. So, with that, I'm going to start by trying to motivate the difference between how a speaker works and an instrument works. So, when Pong plays the violin, come in the middle. Can you play a bit louder? Great. So, just this little instrument right here is able to project sound and fill an entire room this big. A speaker, on the other hand, when you're in a concert hall, you might have noticed that a soloist is able to fill a concert hall without any amplification. But when they need to make the announcements, they need to have speakers located all around the room. And that's because an instrument is able to propagate sound in all directions. A speaker, on the other hand, is very, very directional. So, I have here a speaker. So the way an instrument works, in this diagram, you can see that the violin is able to propagate sound out in all directions. And this is what we call directivity. And directivity will become very important later in the presentation. Contrast this to a speaker, which I have here, where it sends out sound only in the direction that it's facing. So everything that you hear only comes out in one direction, which is the direction that it's facing. More importantly, the violin body also sends different frequencies in different directions. What I mean by that is, if you look at the diagram here, lower frequencies, 200 to 500 hertz, actually emanate in all directions from the violin, whereas higher frequencies actually only come out from the front of the violin. These frequencies, in turn, bounce off the room and then enter your ear. But because these different frequencies are traveling in different directions, they interact with the room, and then you hear the sound of the violin. Contrast that to a speaker, which sends all the different frequencies in only one direction. So that's a big reason why instruments and speakers have very different physics behind them, and therefore sound very different. So my idea was, well, is there a way we can combine the best of both worlds? Is there a way we can invent a system that preserves the acoustics of the instruments, that preserves the mechanics of the instrument, the fact that it sends sound and sends frequencies in different directions, but at the same time have the convenience and flexibility of a speaker system that you can literally just plug into a computer and treat like any other speaker system? And to do it in such a way that, for example, there is a violinist playing all the way in China, I could tap into his stream that's been uploaded online, and I can just connect this to my home system and hear the performance exactly as I would have if I was sitting right there in the concert hall. So, in order to make that happen, we must first understand how instruments generate and make their sound. And we start with the vibrating string. So on the tables in front of you, I put some rubber bands, and reach out and grab one. I'm going to take one. And I want you guys to... You've done it. All right, and what I want you guys to do is to stretch the rubber band like this and pluck it. Great. So, volume-wise, from 1 to 10, are we going to give it maybe, how many people say this is about a 1? 2, 3. Who thinks this is a volume of a 10? Okay. Now, hold the rubber band close to your ear and pluck it. Can you hear a sound? Yes? That, my friends, is the sound of a vibrating string. Let's contrast. Now, contrast this to a string which has been attached to a wooden bar. From a loudness scale, from 0 to 10, who's going to put this 1, 2, 3, 4, 5, 6, 7, 8? Okay, cool. So we all agree that a string attached to this wooden piece somehow makes it louder. And this is a very important concept. It's a misconception that when people think about instruments, we think about the vibrating string. And there's a misconception that it's the vibrating string itself that is moving the air, and it's that you're hearing. That's not entirely true. A vibrating string on its own, the string itself is very, very thin. And sound is all about moving and vibrating air. The string has a very, very small surface area. So when you're plucking it, you have to hold it really close to your ear to actually hear a sound. But when I pluck a string that has been connected to a rod, you guys can hear the note perfectly fine. That's because the string has now been coupled to a larger surface area. And the sound that you're hearing is the collective vibration of this entire wooden piece and the string. Without the wooden piece, you wouldn't be able to hear the vibrating string. Is everyone on board with this? Cool. So we can pass this along too. So we can extend this concept to instruments like the guitar. So a guitar works on the exact same principle. So we started off with a string connected to a body, and it's the body which basically amplifies the vibrations and allows you to hear it. If we move on to an even larger body, for example, a guitar, the same amount of energy that I pluck produces a much larger sound, thanks to the larger resonating body compared to that wooden slab. I will not be playing anything though. And armed with this information, whenever you look at string instruments from now on, even if it's a completely foreign instrument, for example, from my home country in Thailand, you can actually pick out how the instrument works. So for example, this is a Thai fiddle, but you'll see that the physics remains exactly the same. You've got a string that has been coupled, in this case, to a coconut. And the coconut performs the function of the vibrating piece of wood. So I'm going to pass this around this way, and pass this one around this way. So this one comes from central Thailand, and you'll notice that, again, you have a string that's been coupled to another bigger coconut. Now, through trial and error, instrument makers have been really, really smart with one thing. The transfer of energy, the transfer of this vibration from the string to the body, when you're doing it using the plank, whereas the plank, this is actually very, very inefficient in transferring the vibration of the string to the wooden slab. So what instrument makers have done is they found out that if you add an extra component called a bridge, you can greatly facilitate the transfer of the vibration from the string to this larger body. On a guitar, for example, the bridge is this part here. On the Thai instruments that I'm passing to you, you'll notice that there's a little dent or a little ridge that comes up, which functions as the bridge. And it is the bridge that basically takes the energy from the string and efficiently transmits that energy to the body. In the case of the violin, we have a really special shape. So the bridge, this is the bridge of the violin. If you don't get me to show. It's okay. It's okay. And the bridge of the violin is a fascinating piece of engineering. The most amazing thing about it is that it came to its shape through trial and error. But when you look at the physical properties of it and look at the things like frequency response, it has these wonderful properties that, unfortunately, we won't have time to go through in this presentation. But if you're interested, I've quoted a paper that researches exclusively this, the behavior of the violin bridge. And also, I've also wrote up about this on my website. But for those of you who are interested, the bridge basically has its own eigenmodes of vibrations and has its own frequency response and actually filters the signal from the string. Again, if you're interested, I direct you to these links. So anyway, back to the violin. So we have a bridge that's taking the vibrations of the string and communicating that vibration, transferring that vibration to the body of the instrument. Then the body vibrates. And the body of these instruments are very, very complicated devices. They're not just a simple wooden slab like we were passing around. They're not a coconut, but it's a hollow body that's been shaped in a particular way. And it turns out that the patterns of that the body of the instrument vibrates in a very specific pattern. This has been generated using a process called interference holography, and you can see where the nodes and antinodes are. These are basically points where there's maximum vibration and no vibration. So here you can see that this point is going to be vibrating inside out like that. Also, we can also see how the body of the instrument will vibrate using what are called Chladni patterns. And for this, we'll be using this demonstration here. So if you can't see, you might want to stand up. But what we're going to do is we have a violin plate, a pseudo-violin plate, that has been attached to a mechanical vibrator. And when we turn this device on, this device is generating a frequency, which is moving this panel up and down. So this panel will be vibrating at the frequency generated by this function generator. Now, the cool thing is, when you start putting little pieces of salt onto it, you can notice that the salt forms into very, very specific patterns. And that there are points where on this panel, the violin panel is moving, and at other points it is not. And as I sweep through the frequency, you can see these patterns shift. So this is a little bit off. You can add a little bit more there. So you can spend hours playing with this. You can sort of bend the shape a little bit. Okay, cool. So, thanks to these very specific vibration patterns on the body of the instrument, the violin is able to sound the way it does. And yes, oh, here it is then. Cool. All right. So now we can appreciate that the way the violin generates sound is sort of a three-step process. You have the vibrating string, generates the initial vibration. It then transfers this vibration to a bridge. The bridge is connected to the body of the instrument, causes the body to vibrate in very, very specific patterns that we're able to see using processes like the Chladni patterns. And then you get the output, which is the sound of the violin. What I was interested in is, well, if we understand that this is the way that a violin works, is there a way that we can sort of hack into the instrument at a particular location in the signal flow? So what I decided to do is, well, instead of using a vibrating string, can't we just introduce artificial vibrations and vibrate the violin in the exact same way that the string would, but do it without a string? So in the demo here, you'll notice that there are no strings on the device. Instead, what I have is a bridge that is attached to an actuator. An actuator is just a fancy name for a speaker without a cone. It's just a device that vibrates up and down according to an electrical signal. And I have some here that you can see. So it's basically a speaker without the cone. There's an aluminum adapter, which is sandwiched onto the bridge. And what I do is I take the signal from the bridge of another instrument. So this is the signal of the generated by the string before it hits the body of the instrument. I'm taking that signal and I'm sending it into the actuator, which is here, and moving the bridge of my instrument in hopefully the exact same way that the bridge of this instrument is moving up and down. And the demo that I showed you early on basically uses this principle. The idea is that using this method, I can capture the sound from the live violinist, take their bridge signal, send that anywhere in the world, actuate the bridge on my surrogate violin in the exact same way, and hear the instrument exactly as you would have heard if you watched the instrument live. So basically allowing you to experience the sound of a live concert anywhere in the world. So right now, the device, as you've heard before, sounds something like this. And if I remove the actuator, this is all that you hear. And this is the raw signal that comes from the bridge of the instrument that I recorded. But the minute you put it onto the body, basically the body of the violin vibrates, and you get the sound of the violin. So it's basically mimicking how the strings would vibrate the bridge, but doing it instead with using it through artificial means. And this is really exciting because it means that it means that theoretically, if I had 40 of these in China and then had 40 pickups connected to the Yale Philharmonia, we could stream the entire Yale Philharmonia to any country in the world and have it sound exactly the same. We can also put a lot of violinists like Pong out of business by employing only one violin and then sending the same signal to a bunch of surrogate violins. And a lot of violinists like Pong and Rita have been very angered by this, and I usually just tell them that it's not my problem because I'm a pianist. So, right now I'm working on a new design of the device, which instead of taking the signal from the bridge, actually takes the signal at the interface between the bridge and the body of the instrument. Right now, the problem with this design is that the entire bridge is being moved up and down at the same time, so that the 2 feet actually move up and down at the same time. Does that make sense? Because the actuator is clamped onto the bridge. In reality, the 2 feet of the violin actually move up and down at different rates. Sometimes they're moving up and down together. Sometimes they're moving up and down like this. It's kind of like a dance. Sometimes it's just moving up and down like this. And to be able to account for these differences, the next version, the Surrogate Soundboard 2.0, will have individual actuators on both sides of the bridge so that I can individually actuate each feet of the bridge. And hopefully, figure out a way of making sure that whatever signal I pick up here that's happening on the live violin, once it's been transmitted to my surrogate instrument, if I look at the exact same location, hopefully these signals will look the same. At its current stage, even though it kind of sounds like a violin, when you look very carefully at the signals that are being generated, it's not quite there yet. And what I hope to do is to find a transfer function, which is just a fancy way of saying, find this thing here, which when I pick up the signals, corrects the signal in such a way that when it goes into my system, which is sort of a modified violin, it will still behave exactly like a violin. Right. Now, another cool ramification of this device, though, right now, I've just been talking about trying to stream a live violinist to another violin. But what if we actually did not use a violin and use something else entirely here? So, for this demo, this is a violin that Pong has designed himself in Larry Violin and Conrad Kaczmarak's class ENAS 344, Music 371. It's called Instrumental Acoustics and Design. It's a really awesome class. And do you want to maybe talk a little bit about your violin?
So I just laser cut it and stuck it together. And so it doesn't have a body. So when it makes sound, I still can't really hear this. It's a bit thin. So I can play soft like a cello.
Cool.
Yeah.
So let's kind of call this the mediocre violin. Now, what if I now, instead of taking the signal from maybe another very, very high-end violin, I take the signal from a DIY violin that Pong here has constructed in the CID and pass that into my violin system here. So we're going to try a demo, which I've not tried before, so it'll be really interesting. You want to move, maybe move a little bit back.
Okay. So I'll move further back.
All right. Maybe here. Got it?
Yeah.
All right, is the transducer in? Maybe I should show the audience. So what I'm doing, this is what's called a transducer. It basically sits on the bridge of the instrument right here, and it picks up the signal from the bridge, and we're just connecting it to the bridge of Pong's instrument. All right. Then we're going to take that bridge, send that signal into my computer, and then send that signal into the surrogate soundboard here, and see what it sounds like. Okay, so keep playing. So this is the sound of Pong's DIY violin, just playing on its own. Now, I can turn up the signal, have more of it come out through the violin. Sounds pretty good. It's kind of getting there. Not perfect yet, but what this allows me to do is another exciting thing. So, Pong, maybe play like a high note. Too high. Too high. I can actually play around with the tone of the violin. So just sustain the note. Sustain. So here I'm increasing the high frequencies, and I'm turning them down. Here I'm turning up the lower frequencies. Cool. All right, thank you. So this is very exciting because now that I'm in absolute control of every point of the signal chain, down to when the string is vibrating, to when it hits the bridge, I can send it into my computer, I can tamper with the signal. I'm in full control of how this instrument works, which means I can change the sound of this instrument to my liking. So I was able to amplify and tune and modify the sound of Pong's DIY violin in my system and kind of get a better sound out of it. And this is interesting because, well, what's the value of a Stradivarius now? You can kind of model it yourself. We'll be talking about that a little bit later. But for this project, I'd like special thanks go to Professor Roman Kutz for his enthusiasm and guidance on this project. I met him when I was in sophomore year, and he's been a wonderful mentor in all of my projects. Professor Larry Violin helped me construct, design, and machine all the different parts in this project. Nancy, she was the lady who works at Audubon Strings, and she was the person who helped me figure out all the violin things, what I needed to buy, where to buy it, can you give me discounted price, 20% off. She was in charge of all of that. Professor Douglas Stone for initial funding, and the Franke Fellowship in Humanities and Sciences, which is a new fellowship, and has funded the additional materials that I use to bring this project to fruition. Also, Victoria Wepler, who was the first person to test and give me musical feedback and do all the recordings for my signal analysis. And also Rita and Pong, like violinists. And yeah, I like my brothers and sisters. So, we're now going to maybe lead into some questions. And I'd like to maybe prompt you with some questions that I've been thinking about regarding this project. what is a musical performance? So this is getting kind of philosophical, but when you're watching a performance or you're watching a stream of a concert through your computer, of course it doesn't sound like it and you know they're on their screen. But what if you went to a string quartet and you went to the School of Music Hall and you sat down and there were just surrogate cellos, surrogate violins, surrogate violas on stage, and you listen to it, everything is exactly the same, it sounds great, you recognize music, it moves you, but is that still a musical performance in the same way that a musical performance is when there are musicians on stage?
You guys can.
What about the fact that many of us, when we go to watch concerts, even if there are musicians on stage, sometimes we just close our eyes. I know many people who just close our eyes when we listen to the music and just experience the music as a sonic event in itself. And it's not so much about the physical presence of the musicians. In that sense, does a system, if perfected this way, is that still a musical performance, or how much of a musical performance is it? How can this technology complicate, for example, the value of a Stradivarius? Now that we're able to tune, fine-tune, and hack the signal of the instrument, and I'm able to tune a DIY violin to something that sounds 10 times much better, 10 times more expensive, not even 10 times, 10,000 times, and 10 million times more expensive than what it actually is. How does this change the way we value certain kinds of instruments? How does this change the value that we impart on certain kinds of instrument-making traditions? Because, for example, the value that we now have on vinyl discs, the value that we have on cassettes, on CDs, these previously tangible mediums of experiencing music have gone down significantly because of Spotify, which is great. Well, no, Spotify is great, but vinyl going down is not as good. And also, if this technology goes forward, or when this technology goes forward, would our grandchildren pay to go see a surrogate orchestra? Would it be considered normal and actually fun and okay, like I'm going to go see a live stream of the Yale Philharmonia in Shanghai, but it's a surrogate orchestra? That's totally cool. Like, I do that. So with that, I'd like to put the presentation to a close and open up the floor for questions. Thank you.
Sorry. Not sure how to ask this, but so, other than maybe some university in Beijing would want to, I don't know, have some like surrogate orchestra, who do you think would be interested in like purchasing this kind of technology if it were ready?
So definitely concert halls around the world, for example, this would allow you to basically not have to wait for an entire orchestra to come into the orchestra hall to perform. And you can just have sort of concerts of a certain orchestra that's located in another country, but have it being performed in your concert hall with the same acoustic benefits of being at a concert. This also has uses, for example, as a teaching tool, perhaps, for long-distance lessons, as opposed to having violin like coming through a phone or like a computer. You can actually have a system like this set up at your in your own home. Another interesting thing is definitely in the professional audio industry, strings. I don't know if any of you make music or have listened to computer-generated strings, because they sound absolutely horrendous. Despite our advances in signal processing, we haven't been able to accurately model and generate very convincing string sounds. And so when you hear, like string sounds in like movies, you can tell when it's not a real violinist playing, right? Like when you see in like dramas and stuff like that, when they can't afford a real violinist, they just kind of use the computer-generated ones. What this would allow you to do is, I could have the signals instead be generated by a keyboard, and then you can play the sound, but have it come out of the physical instrument, the physical violin, and mic it any way you want, and not be stuck with a computer-generated sound, but actually have the physical benefits of a live instrument without having to pay or wait for a violinist. So that's definitely another usefulness of it. And with this project, the physics of many string instruments are very similar. As they have a lot of shared characteristics. So this kind of system would work on, for example, the Thai fiddle that I just showed you because of the exact same physics. It would also work on guitar because there is a string, bridge, body mechanism. I happened to pick the violin in particular because it was an instrument that I was interested in. But in making it work for the violin, you can cross this technology and apply it to a much larger field, larger family of instruments.
Sorry, I just wanted to follow up. So say that you had, you wanted to place on a violin and get the best sound possible. Would you still have to buy a Stradivarius to put that in that? Mimic the sound, or could you compensate for that?
Exactly. So this is the exciting part. So when I was turning the knobs here, I was tuning the signal that was coming into the violin, and then tuning exactly how this violin sounds. So if I know what the sound of a Stradivarius is like, I can find things like its impulse response, I can find its frequency response, and I can model theoretically, hopefully it'll be physical, because that'll be really cool, but theoretically model the system using a much cheaper violin, but have it sound much closer to a Stradivarius. So you wouldn't need to get a Stradivarius. But there's also a flip side to that, interesting flip side. A lot of people want to play on these beautiful instruments, but can't. What if you just had one sort of Stradivarius sitting on its own, and then many people around the world can play and tune into that instrument, a little bit like how you have like telescopes in the sky that people can access through the internet and get their own pictures. You can almost crowdsource, like you can open up an instrument that many people would never ever in their lives have an opportunity to play, be able to play. So that's another interesting flip side to that situation. Yes?
So you sort of just mentioned using other inputs of sound and then playing them on the violin, like the piano.
Yes.
Have you tried that?
So, yes. It sounds kind of weird. I've also tried playing music through the device, and it also, well, I can show you what it sounds like. It basically just sounds like a song that has been passed through the frequency response of a violin. So it will not sound like a speaker, and it will sound like a really crappy speaker because the violin body is not designed to handle frequencies across the entire hearing range. But you can play something like. Oh, okay, no wait, this is not set up to do that. Maybe later. But to answer your question, yes. So I have passed like guitar sounds through it, for example, and it's a really cool effect. It's interesting because you usually associate the sound of the guitar with the body of the guitar, but using the system, you can basically mix and match the bodies of different instruments. Previously, you were able to do this in software. You have a very, very accurate computer simulations that said if you took the string of a cello, wrapped it around a saxophone, and then stick it to the body of a violin, this is what it would sound like. If you then stuck it to the body of a guitar, this is what it would sound like. But this allows you to do the physical version of that and actually play on a guitar, take the signal from a guitar, and then pass it into the body of a violin, but do it all in real life, which is kind of cool. Yes, in the back.
A lot of violinists would say that the quality of your bow matters as much, if not more, than the violin itself.
Mm-hmm.
I just wondered if you'd experimented with that at all. What effect does bow quality have on sound production, and how can you model that?
Sure. So the bow definitely does have a very important part to the sound generation of a violin. But the interesting thing is, when you bow onto the violin, the signal is generated in the string, and then the signal goes to the bridge, as we previously discussed. And at that point, because I'm taking the signal from the bridge of the instrument, any variation in bow has been accounted for by the fact that I'm picking the signal here. So if I change the bow, the signal in here will change. I will pick up a different signal, and because I'm picking up that different signal, I can account for the change in bow. And work around it that way. Yes?
Theoretically, could you apply this broad technology to non-string instruments? A reed, for example.
Yeah, so this is a very interesting question. So yes and no. For string instruments, hopefully I've shown you today that it is possible and that we're kind of getting there. Well, hopefully I'm getting there. But for reed instruments, let's think of the reed instrument, for example. Think of a saxophone, maybe a clarinet. The sound producing mechanism of a reed instrument, for example, is you have a very thin piece of wood, the reed, that moves up and down. In order to faithfully recreate how the reed works, you would need to be able to faithfully recreate exactly the organ that's directly in touch with it, which is your mouth, and be able to mechanically actuate all the different muscles and all the different mouth positions that go into making that go into producing the sound coming from the reed. So although it is theoretically possible that if you had a system that was able to accurately do that, you'd be able to generate sound, it's extremely difficult. Hence why, in this particular, I was thinking about that, but I went with a violin because, as you can see, any kind of difference, like I can be playing harder, I can be using a different bow, I can be plucking it, as long as I pick up the signal from the bridge, I can pick up all those different changes and account for those different variables. It is very hard to do with, for example, a reed instrument. Yes?
So when a professional musician plays on a $100 violin, it sounds a whole lot different than when that same musician plays on $1 million violin. Have you like thought about that at all? Like as like a complication to your whole thing that like a $10 violin could be tuned to sound like a Stradivarius? Because I feel like for a violin that's of low quality, there's kind of this upper limit to how good the sound can be. Because like for 300 years, instrument makers have been trying to emulate the sound of the Stradivarius, right? But it could be argued that none of them have actually been able to do that, even though they're working with, high quality materials, the same design and all of that. So.
So I think your question comes in two parts. So I think that a professional violinist who is able to breathe more life, who's able to make a $10 violin sing in a way that you never thought it could, I think a lot of that has to do with the ability of the musician, as opposed to just like sorry, wait, can you repeat your question again?
Yeah, so like the same violinist playing would theoretically play the same violin, or two different violins in the same way, right? So theoretically, like what I'm imagining you're saying is that they would get the same sound from two different violins, even though violins themselves are different.
Same sound from two different violins.
Because they're playing them in the same way, right?
But the violins would sound different. If
Yeah,
they played it
exactly.
the same way and then the two violins were different, the sound that they would get would be different.
Right, yes.
Okay.
But what I was imagining you were saying was that when somebody on one end of this system were playing the violin,
Yeah.
and then it came through on a different violin, it would sound different, right? So in order to get the same quality sound out of the other end, you would need to have a violin of equal quality to the violin that was being played on.
Yes, okay, I get your question.
Okay.
Okay, great. So, yeah, so basically what I hope to be able to do is, yes, so if we had equal quality violins on both the transmitting end and the receiving end, and everything was done right, it would sound exactly the same. The idea with this is because I'm now because I have full control on the signal that I'm taking from the initial violin, I can tamper and change it in a way that any deficiencies in the receiving instrument, let's say it's not as good as at propagating high frequencies, I can boost up the high frequencies and make up for that. So I can make a worse sounding violin, not as good violin, for example, that's lacking in certain warmth characteristics. I can return those qualities back in, so we wouldn't say return the qualities, but basically tamper with the signal in such a way that it takes that into account. So that you could technically tune a much cheaper instrument to have a better sonic characteristic that was closer to that of the source instrument. Now you also asked a second question, which I was going to answer, but then I stopped. But okay, anyway.
You did fine. Yeah.
Okay.
Well, I hate to cut this conversation short, but it is time for dessert, and I hope that you will continue to talk with Hanoi about this amazing project that's really got us all thinking about, I think, physics and music in completely different ways. So thank you so, so much. Thank you also for being one of our first presenters. We're very, very grateful. You've really both of you today have really led the way for us in thinking about our disciplines in really new ways and opening up the way we think about technology and sort of beauty in our world and the way we interact with each other in just really new and exciting ways. So thank you so, so much. Please, everyone, help yourselves to dessert. Speak with our presenters. Next week, we have Ethan and Dina who will be presenting. So I hope that you will join us on November 4th. All right, thanks, everyone.